All right, trig folks, I was asked to do a short presentation on section 6.1. One of you asked me for a little more explanation, so I thought I'd put something together. 6.1 talks about inverse functions, and I know it's a little fuzzy, but we'll do the best we can here. So we start with a trig function like the sine of x, and as we know, the sine of x would actually keep going down, and it would hit pi, and continue on and on and on. But what we're going to do is, instead of having a domain of all the reals and a range from -1 to 1 for the sine of x, we're going to now cut this off to just this section. And the reason why is when we're going to do an inverse function, we need to make sure that we maintain one-to-oneness, a term that you may have heard before. So let's go back and do a quick review of something that in algebra you would have done an inverse of. An inverse starts out as a function like y equals equals 2x minus 1. And we're used to seeing f of x equals 2x minus 1 as well. So basically, if I put in a value for x of 2, 4 minus 1 is 3. Now, when I'm dealing with an inverse, what I know is my x and y values are actually switched. So in order to calculate the inverse, I'm going to switch the x and the y into my equation. Now I'm going to solve for y. I'm going to add 1 and divide by 2, and I get the new equation y equals x plus 1 over 2. So if I put in what was my range value is now my domain value. 3 plus 1 is 4 divided by 2 is 2. So you can see whatever I put in here goes to 3. Whatever I put in here 3 goes back to 2. And it's an inverse. So we end up with f inverse, that little -1 superscript of x, would equal x plus 1 over 2 in this case. Now, if I graph an inverse, quick refresher on graphing an inverse is I'm going to have symmetry over the line y equals x. So what would be at the point 2, 0 would now be at the point 0, 2. If I had a shape that maybe goes that way, I would have to have it symmetrical over a shape that goes that way. So when we're talking about inverses, the domains become the ranges and the ranges become the domains. If I look at it graphically, it's symmetrical over the line y equals x, 2, 0, 0, 2. So let's go back up to our trig function, y equals the sine of x. And in order to get this one-to-oneness, I'm going to have to take this domain, which was all reals, and I'm going to change it to -pi over 2 to pi over 2. And the reason is, if I kept going here, I would have a repeat. If you remember from when you were doing this algebraically, we had to pass the vertical line test. Every x has only one y. So when I start talking about inverses, I need to pass the horizontal line test. Every y has only one x. And again, it's to ensure this one-to-oneness. So if I start by restricting the domain and the range, I now have a range that's -1 to 1, and I have a new, domain, and I have a new range, which was the old domain, from -pi over 2 to pi over 2. My first point here was -pi over 2, -1. So if I switch it, it's now going to be -1, -pi over 2. And if I kept plotting points and plotting points, what I would end up with is a graph that looks like this. And that would be the graph of y equals the inverse sine of x. Okay? Coming back over here, let's take a look at what my domain values are. Okay? My domain values are going to be from -pi over 2 to pi over 2. Now, if I thought of that on a circle, I'm looking at 0 to pi over 2, and -pi over 2 would be this region. So when I'm working with a graph and its inverse, I need to think of values where all of my positives for sine are in quadrant 1, and all of my negatives for the inverse sine are in quadrant 4. So that's the reason we get to quadrant 1 and 4 when I'm dealing with the inverse sine. The inverse cosine is going to be a little different. It's quadrants 1 and 2. Because when I look at an inverse for cosine, I look at, well, a cosine starts here and goes to there. It goes from 0 to pi for my inverse cosine. So 0 to pi over 2 is quadrant 1. The values pi over 2 to pi is quadrant 2. So my positives will be in quadrant 1, my negatives in quadrant 2. Tangents, the same kind of deal. Positives, all of my positives are quadrant 1. My negatives, just like sine, are in quadrant 4. And I'm going to show you a quick question, problem example that will help a little bit with this. Okay, so I want to take a look at the sine of the inverse tangent of 3/2. Now, when I'm doing an inverse tangent here, this guy, an inverse, is going to result in an angle. Just like before, when I did the sine of an angle, like the sine of 30 degrees, I got a value out of it. So remember, these guys are being switched. Angles and values are being switched. So when I do the inverse tangent of 3/2, I'm going to be getting an angle measure out. Well, I don't know what that angle measure is, so I'm going to call it theta. And I'm actually going to put it on this graph. Theta equals tangent. So the tangent of theta is 3 over 2. Completed is square root of 13. So whatever this angle measure is, I don't know, and I'm not going to put it on a calculator. I'm just going to represent it and say, hey, this is the angle up here. Because remember, the inverse tangent of theta over 2 is going to equal theta. And if I brought it over, the tangent of theta equals 3/2. So the tangent of theta equals 3/2. Now, I know this is an angle measure, that bad boy right there. I'm going to take the sine of that, 3 over the square root of 13, and I'm going to rationalize it to get a final answer of 3 square root of 13 over 13. Now, what if I would have done the sine of the inverse tangent of negative 3/2? All right, so now I need an angle measure. Because this is negative, I need it to be in not the first quadrant, but a quadrant where tangent's negative. And I said before, when we're dealing with inverses, the tangent is going to be negative in quadrant 4. So I'm going to come back up here. I'm going to think of this as the sine of theta again. I'm going to put theta this time, quadrant 4. Here's theta, quadrant 4. The tangent is negative 3 over 2. Completing the triangle, that would be the square root of 13. So now when I want the sine, I want the opposite over hypotenuse. It's going to equal negative 3 square root of 13. And again, when I rationalize it, I'm now going to have negative 3 square root of 13 over 13. So I hope that helps, maybe fills in a blank or two for section 6.1. Again, if you have questions or you want an explanation, let me know, and I'll gladly make a video with my voice, and I'll send it out to you. All right, have a good day.